here today, who is Roberto Cominetti. I'm very happy to introduce him. He's a professor at the Universidad Adolfo Ibáñez in Chile. And well, of course, you all know him very well, I guess. And oh, is that your screen, Roberto? Yeah, perfect. Okay, so Roberto is going to speak about large routing games, but I don't know if he's here again. Yeah, you're muted. Yeah, perfect. Okay, thank you very much. So it's your give the floor to you, and well,
okay,
the screen is yours.
Okay, thank you. Thank you for the invitation. I'm very happy to be with you, and unfortunately just online for over 2 years now. But okay, that's how things are currently. So the talk I'm proposing today, it's somehow recent work we have done with my colleagues Marcos Carcini, Mark Schroeder, and Nicolas Stier-Moses on game theory, but particularly focusing on games where there is a huge or very large number of players. And as a motivation, I will concentrate on routing games. And I want you to imagine that you're planning your trip from home to work tomorrow. You're not really sure at what time you will leave. And of course, you're not sure who will you find on the road. So you can visualize this as a game with many players, but in fact, the players that you interact with is just a subset. It's a small subset. So just to give you a rough idea, if you look at Santiago peak hour in the morning, there are about 2 million trips or 1 million trips, depending on the time. And naturally, I will not be interacting with all those cars on the streets, okay? So depending on your precise time where you live and when you reach the network, you will find a small subset of players. You don't know who this will be. So you can visualize this as a game with incomplete information. And the incompleteness of information comes from the fact that you don't know exactly who you're playing against. One day can be one subset, one day, the next day could be a different subset. Now, the standard approach made by civil engineers from, since the 50s is to visualize traffic as a continuous model. And this is the notion of wardrobe equilibrium. And the question we're trying to address here is precisely what is stated in blue. If there is a way to justify the wardrobe limit and to measure how different would be from the discrete real model. That's the question we want to address. In other words, what is the meaning of a wardrobe equilibrium? What is the meaning of a game with a continuous of players? And the answer turned out to be somehow tricky because it depends on what do you understand by a small player. There are two ways, at least, to understand what a small player is. The standard or the classical one is the first over here. It says that a player is small when it represents a very small fraction of the traffic. So basically, it's an atom, or it's a drop in the notion of players. So you identify size with the relative weight of a player with respect to the global traffic. But there is a different way of interpreting a a player to be small is to say, okay, a player has the size which it has. A car, it measures 4 meters, not 0 meters. But a given player might be present with very small probability. Now, if you focus on a very, let's say, 5-minute period during the morning peak, the probability that I will be there, or that Juan Peipunque or that Matias will be there, I can consider it to be a small parameter. Probability that me and Matias, we coincide at a given time and we play against each other is very small. So in this sense, you can think of a small player as a player who is active in the game with a small probability. And somehow surprisingly, the two interpretations of what a small player is lead to different continuous limits, and this is what I will try to explain. In fact, I can give you a flash forward here. For the first interpretation, so when you consider a limit game, where you increase the number of players and you reduce the size of each player, you end up with the classical wardrobe model. When instead of that, you consider, again, an increasing number of players, but decreasing probabilities of being active, then you reach a different type of limit, which is a Poisson game, in the sense of Meyerson. But it's not completely disconnected with wardrobe. In fact, the Meyerson-Poisson model has a connected, has an underlying wardrobe game. And this is, in my view, a quite interesting interpretation, which in fact fits well with the data. Okay, after this sort of long introduction, let me state more precisely notations and results. So we work on a network, on a graph, which nodes denoted by V, edges by E. Every edge is endowed with a cost, which is assumed for simplistically continuous, non-decreasing. And moreover, over the graph, I have a family of origin-destination pairs, each one with a set of routes. I will denote R for the routes, kappa for the OD pairs, and each of the pairs has a traffic to be routed from origin to destination. In this example, there are two origins, a single destination. And routing games differ on what do you assume with respect to the demands or the traffic demands. In the non-atomic model, you imagine that this demand is formed by infinitely many players, each one negligible in terms of volume. And this leads to the wardrobe model, which I will summarize in the next slide. On the other extreme, you have atomic games where you have finitely many players. And again, you have basically three types of submodel from the atomic point of view. The splittable one is when each player controls a demand DI, but this demand DI can be split across different routes. So I can route my demand over multiple routes if I want, one half here, one half there. So basically, I'm transporting something like a fluid or sand. And this is in contrast to the unsplittable case where I have a certain volume to ship, but I'm forced to assign it to a single route. I cannot split, let's say, a vessel or an airplane over two alternative routes. So every player has a certain flow, but in the unsplittable case, you have to commit to a single route. And then there is the random presence of the player, which is the model that we're going to address later. So these are the two main areas, non-atomic and atomic, and the atomic has three versions. So how do you model non-atomic wardrobe? This probably most of you will know this very well, but let me just, for stating the stage and the notations, how do you modelize a non-atomic wardrobe equilibrium? Namely, you take your demands decay, and for every origin destination pair, you split the demand decay across the feasible routes for that origin destination pair. So you consider these variables YR, which are route flows. So you split your demand, and then by simple accounting, you look at every edge and you sum all the flows that go through that edge. So this is simple accounting. So every splitting I will denote by F the set of feasible route flows and corresponding edge flows that satisfy these linear constraints plus non-negativity. So it's a nice polyton. And then the model proposed by Wardrop is the definition of a wardrobe equilibrium is that you're looking for a feasible splitting of the demands such that only the best or shortest routes are used. And this is written over here. We say, for every fixed origin destination pair, if I look at two alternative routes, one of which, let's say route R, carries a positive flow, so somebody is using, or a fraction of the flow is using route R, it should be the case that the cost of that route is better than the cost of any alternative route R prime. And the cost of a route is expressed as a sum over the, imagine that these are travel times. So if I want to, I will sum up over all edges of the route, the travel time of that particular edge, which is flow dependent. And it turns out, this is very well known, it's Beckman, Maguire, and Weinstein, they proved in, or discovered in 1956, that these equilibrium conditions are nothing else than the optimality condition of this associated strictly convex, or at least convex optimization problem. So if you write down the optimality conditions for this convex program, you get this, and these are equivalent. So that's the standard model that has been used for over 7 decades already. So let me go quickly about atomic split-level routing game. I will really flash because I want to get to the random case. So in a atomic splittable, what you have is a finite number of players. Each player has a demand, a traffic demand, has an origin destination pair, and each player can split the demand throughout the available routes. So each player can induce this route flows, induce edge flows, and then player I can compute the cost, the total cost, by just multiplying the flow on the edge times the cost on the edge, which depends on what player I is doing and what all the rest of the players are charging on edge E. And of course, a standard notion is that a Nash equilibrium, in this case, a splittable Nash equilibrium, is just a family of feasible flows where each player is minimizing her cost. So nothing fancy, nothing new here. Now, existence for this type of games were proved by Rosen in '65 and proved uniqueness under suitable monotonicity condition. Now, what I'm more interested in what is the connection between this notion of Nash equilibrium for the splittable case with Wardrop. And what you expect is that if you increase the number of players and each player becomes smaller and smaller, then we should be close to a Wardrop equilibrium. And this is exactly what Henri Marcotte proved in '85, then extended by Milteich 2000, and recently Jacob Wan in 2018. And they have different conditions under which this theorem is true. So basically, this is the formal statement. You consider a sequence of games and a sequence of equilibria where the number of players, so this is the set of players of the nth game. For the nth game, you have this. You have the number of players that goes to infinity. The maximum size of a player goes to 0. And the aggregate demands, if you aggregate all the players that are traveling on a given OD pair, so if this aggregated demand converts to a certain decay, then what you have is that the flows, the route flows, the aggregate route flows, and the edge flows remain bounded. Every limit point is a Wardrop equilibrium, and everything is nice. So these results, I say that it is expected. After all, the only difference between atomic splittable and non-atomic is that the players are smaller and smaller. But the equilibrium, you see the equilibrium here in the atomic splittable, in the equilibrium in a Wardrop game, they live in exactly the same space, the space of route flows and edge flows. So a certain RD with some dimension D. So convergence is just standard conversions in Rn. The thing changes quite a bit when you proceed to atomic but weighted congestion game. So the unsplittable case. So if you go to unsplittable, then your strategies is no longer a splitting of the flow. So you're not controlling a flow, you're controlling a route, which you choose at random. So here's the setting. In weighted atomic routing games, you have finitely many players. Each player comes with a particular OD pair, but now the weight, WI, has to be routed over a single path. That's the main difference. And the path you use, so all your weight, it will be assigned to a given path, and this path you're allowed to randomize. So usually you proceed not to pure equilibria, but to mixed equilibria, where players are allowed to choose Ri according to a given probability. And this vector of probability is the mixed strategy of player I. Well, when you try to fit this with the non-atomic game, so Wardrop equilibrium, you have two difficulties. One is the passage from a finite to an infinite number of players. But the main difference is that the notion of equilibrium, they live in quite different spaces. One is the space of flows. Here is the space of probability measures over routes. So how do you make the connection? Well, by looking at the induced flows and the use edge loads. So basically, when players are randomizing, what you observe is that the route flows become random variables. Basically, since if I look at a particular, let me make it bigger here. If I look at a particular route R, and I look at how many players or how much weight is assigned to that route, well, I have to count the route of every player I who is choosing that route. So here Ri is random and is chosen according to a certain probability. So while R is a sum of, these are Bernoullis, which I will assume independent. So it's a sum of weighted Bernoullis. That's the load on a route R. And the same for the load of an edge. If I want to know how many players or how much weight goes on a link E, I have to sum the weight of all players I, but only those players that are using that link. So what about equilibrium? Well, this is the notion of Nash equilibrium that I will use. So a strategy profile of mixed strategies is called the Nash equilibrium. If and only if, again, for every pair of routes, if player I is using a route R, it should be the case that the expected value, or the expected cost in this case, of using that route is better than the expected cost of using any alternative routes R prime. But this is just written in this framework, what Nash equilibrium is. But now, if you want to study the limit of these games when the number of players grows and the weights decrease, WI decrease, you have to study the convergence of this random variable. The best you can expect is some convergence of random variables towards a wardrobe equilibrium. I will skip that one. And just to give you an idea, very specific case, imagine a simple network with just two identical links, two parallel links. I have n players. There are many equilibria here, basically half and half. Any splitting of n into half and half or randomized half and half will be an equilibrium. So in particular, a symmetric equilibrium where every player randomizes 1/2, 1/2 will give you a load on this edge, which is just a binomial and 1/2. And if the weights of the players are scaled down as d over n, so that the sum remains constant, the total weight is n times d over n, that means d, then I have a load, which is the weight of each player times a binomial n 1/2. And of course, this, because of just the law of large numbers, this converges to almost surely, this converges almost surely to d over 2, 1/2, which is precisely the wardrobe equilibrium. Okay, so this basic observation here generalizes to non-symmetric equilibria, different edge costs, general topologies, and heterogeneous players. So it's a very general statement, which is here. So consider a sequence now of mixed equilibria for weighted atomic routing games, where I assume that, as before, the number of players goes to infinity, the maximum weight of every player goes to 0, and the aggregate flows per or destination pair converges. Then what you have is that if I look at the random loads and flows, the expected value of those random variables, this yn, xn, this sequence is bounded, and every cluster point is a wardrobe equilibrium. And moreover, basically, if you take a subsequent where this converges to a wardrobe equilibrium, then you observe that your random variables converge in a 2 to that constant y bar x bar. So basically, what you observe here is that your random variables will converge to a degenerate random variable concentrated on the wardrobe equilibrium. I will skip this. Let me just say that we can measure the error that you incur when you replace the finite game by the wardrobe model. You can estimate exactly the L2 norm of the error you're facing. But I don't know how much time do I have? 5 minutes?
Yeah, 5 more minutes.
Okay, that's good.
Yeah.
So all of this is rather classical, well, except for the last slide. But in practice, this is a bit far away from what you observe on the route. So here's an example or a numerical exercise that we did by just collecting or using data collected in Dublin. So what you observe in these plots is for a certain segment in within Dublin, if you look at every Thursday from 7 to 10 a.m., this 10 minutes time, and you look how many cars go through this, so you count the number of cars, so you look at the flow. What you observe is that this, I think it was data collected for over 2 years. So every Thursday at this precise moment, sometimes you observe a load of 88 up to 166, and there is this type of distribution. So certainly this is far from being a degenerate distribution. It has some variance, and what I'm plotting here in red is the Poisson approximation of this distribution, of this empirical distribution, which has the same mean. And this occurs from 7 to 710, but it reproduces, you know, from different periods of 10 minutes. They show this pattern of, you know, traffic flows that are not concentrated at the wardrobe equilibrium, but they exhibit a sort of variability. So this is what led us to introduce or consider these Bernoulli routing games, which is basically the same as a weighted game, except that the weight of a car is random. Namely, the weight of a car is either 1 if player I is present, or 0 if player I is not present. So you just replace the WI, which were fixed and small, you replace it by UI, which is a random Bernoulli with probability PI. That's the whole change. Except from that, the model is exactly the same as the weighted. So you see the analogy here is very striking. The only thing I did is that before I had a fixed but small weight. Now I have a random weight, which is either 0 or 1 with a small probability. But again, your loads and flows are random variables. And the question is, what is the limit of, how do this limit of these games look like? What is an equilibrium here? Well, as before, this is a game with uncertainty. The uncertainty comes from these variables UI that describe whether player I is present or not. So what you do for computing a biased Nash equilibrium, well, every player will randomize, will choose a route at random according to a strategy pi, which is a mixed strategy. And you choose in such a way you evaluate the expected cost of a route by conditioning on, by taking expectation with respect to the presence or non-presence of other players, and also expectation with respect to what are the random choices of the other players. So you look at these variables XC that depend on everyone. These are random variables. You consider the expected value of the cost of route R, conditioning on the fact that you are present. I'm player I. I condition that I am player I and I am active in the game, and conditioning on the fact that I'm choosing route R. So this is again the standard notion of biased Nash equilibrium. And here is again a very simple example to show the difference with respect to the weighted case. So consider again a very simple network like this, n players. Each player randomized 1/2 is an equilibrium. And if the player is present with probability d over n, now the random loads take this form. These are binomials of n over 1/2 d over n. So the d over n that before was outside, now it comes inside. And naturally, when you get a sum of n Bernoullis with small probabilities, the limit model is a Poisson. So for large n, it converges to a Poisson of d over 2. And I will skip the technical part. I don't want you to look too much in detail to this, but except for the title, to generalize to non-symmetrical equilibrium, different cost, general topologies, and different probabilities for not uniform PIs, but different heterogeneous PIs, we will use known results of approximation of Bernoulli random variables or sum of Bernoulli by Poisson. So these are very classical, some very classical results. I will measure the distance between two random variables by the total variation. So saying that two random variables are close in total variation is a very strong, possibly the strongest property that you can expect between, distance between distributions. And we use some known results. One of them says that a sum of independent Bernoullis can be approximated by Poisson. And the other is related to expected values that also behave quite well when you replace a sum of Bernoullis by a Poisson with the same mean. Well, except for this technical stuff, so what I will do is that to come back to our starting point where the limit, where we're interested in taking limits of Poisson games. So we started from the cost CE that were defined from 0 infinity to itself. In fact, for the unsplittable case, it's enough that the cost is defined over the integers because the loads are all integers. And what I will do is to start from the cost CE and extend them to a cost defined on R plus. So I'm assuming that CE is just given from N to R, and I'm extending to CE tilde. And how do I do that? Well, for every real X, I take capital X are a Poisson random variables, and I take the expected value of this cost. So explicitly, this is the extended cost. And once you have done that, you have this theorem. It tells you that if I consider a sequence of equilibria with an increasing number of players, the probability of presence of each player is going to 0, so it's very small. And the expected demand per origin destination pair converges or stabilizes around a certain decay, then again, your expected flows are bounded, every cluster point is a one-of equilibrium, and moreover, the loads and the route flows converge to Poisson variables where the YR tilde and XE tilde correspond to a wardrobe equilibrium. So that's the connection. So now what you have is that the connection between the Poisson limits and the wardrobe equilibrium is given through the expected value. So you can imagine XE tilde to be, well, it is exactly the expected value of these random variables. Moreover, these Poisson limits YR are independent variables. In particular, if the costs are strictly increasing, then we know that there is a unique wardrobe equilibrium in terms of loads, and you get full convergence of the finite games to these Poisson variables. And furthermore, you can estimate, you can provide metric estimates of the distance in total variation between your finite game and your limit, your Poisson limit, we should say. There exists a very precise estimate. Here, kappa is an explicit constant in terms of the data of the cost and the routes. So just to summarize, what we have shown is that depending on how do you interpret what a small player is, you get to different atomic limit games. In the first case, for vanishing the random loads converging L2 to a degenerate distribution concentrated on the wardrobe equilibrium. For vanishing probabilities, you converge to Poisson random variables where the XE tilde again are wardrobe, correspond to a wardrobe equilibrium. Second observation, the Poisson limit is much closer or is consistent with what you observe in practice on traffic counts. And as I tried to justify at the beginning, assuming that the probabilities are small is a reasonable assumption when you look at a small period of time during the morning peak. Third observation, I didn't talk about it, but in fact, the Poisson limit is indeed a special case of Meyerson-Poisson games, which were introduced axiomatically and for different purposes, for analyzing elections, but it turns out to be equivalent. The framework is exactly Meyerson-Poisson games. And that's about it. So thank you very much. And if I can answer a question, I'll be happy to. Thank you.
Thank you very much, Roberto, for the great talk. And we're now open to questions.
Hi.
Okay, Manuel.
I have a small technical question. The convergence is formulated in terms of convergence of subsequence. Can you imagine formulating the convergence in terms of variational convergences for functions or operators?
I don't think so. I mean, it is possible, it is certainly the case for the first setting where you consider splittable games, because in that case, you're considering two problems that live in the same space.
Yeah.
Okay. Now, wardrobe has a variational formulation, right?
Yeah, yeah.
I didn't speak about that, but maybe it's a good point to make the connection. With variational convergence, what I can say is the following. So you see, in wardrobe model, you have a variational characterization of equilibrium. There are minimizers of this potential function, the sum over all edges of the integrals, of the primitives of the cost. Well, for atomic splittable, you don't have that. There is no potential gain unless the costs are affine. So it's difficult to see how atomic splittable could be treated by variational methods. However, if you go to weighted atomic routing games, you get back a sort of potential. This is Rosenthal potential. So if you look at the unsplittable case with weights which are all equal, let's say, let's normalize to 1 or W, then you can show that if in fact there is a potential. So this is a potential game, so that equilibria or pure equilibria are characterized as the minimizers of this function. Well, you recognize here the integral of the cost over flows. This is a discrete analog. So as long as you consider only unsplittable games with identical players, you may hope to have a variational approximation, except that you will only be able to prove something about the pure equilibrium, which are minimizers of this P. But we know that there are lots and lots of other equilibria where players can randomize. So I'm afraid that it's a different, I mean, if you look at pure equilibria, it's okay. But as soon as you go to mixed equilibria, you're talking about convergence of random variables. These yn, xn are random variables that live in a completely different space than the wardrobe equilibrium. So I don't have a clear view of how you could profit from variation. And the same occurs, of course, when you go to Poisson.
Okay.
You're talking about convergence of random variables to a Poisson random variable in that case. So what is the variational characterization of this Poisson? Maybe there is one, simply I don't know. Wardrobe is definitely stated in a different space. You're talking about reals, real numbers that represent expected values of random flows. So it's an interesting question to see if the Poisson limits have a variational characterization. I don't know. Interesting question.
Thank you, Roberto.
Okay, thank you, Eddie and Roberto. I don't know if there are any other questions or comments. Otherwise, I would like to thank Roberto and also Francesco and all the speakers in the morning. So Eddie, Cora, and Mark. Thanks a lot for being here. And I hope we can meet in person sometime soon at some point, because this is getting a little bit tiresome. So, well, I hope you stay safe and you're healthy, and well, hope to see you soon in the future. Thanks for being here. I don't know if you want to add something, Matthias.
Just reinforce your words. Yes, let's just hope that this pandemic sooner or later turns into an endemic, so that we at least can cope with this virus somehow, with normality, some sort of normality. So I see Mark is doing already the right thing. He's lying at the beach. Yeah, let's do the same thing.
This is my backyard, Matthias.
Yeah, I know already. Of course, I know that already. Okay, no, right.
Yeah.
Thank you very much for being
here.
You
want to exchange with mine?
Thank you, Juan. Thank you,
you.
Matthias. Thanks very much. Thanks for
Bye.
Thank you.
We'll send you a link for the